Now that we've reviewed what the aldol reaction and aldol condensations look like, let's take a look at the target molecules that are related to those reactions. So what are the patterns of functional groups that we'll see? One example is right here, the beta hydroxycarbonyl. So not at the alpha position, but in the beta position, we have a hydroxyl group. So in a case like that, the disconnection we make is right here at the alpha carbon, because the alpha carbon, we know, was our nucleophile, which means the other carbon was my electrophile. It must have been electrophilic, and what did it look like in its starting material? It was a carbonyl. So our retrosynthesis leads back to an enolate as our nucleophile, alpha carbon as our nucleophile, and a carbonyl as our electrophile. That's the aldol reaction. So we could describe this as the Aldol disconnection. And so actually this particular target molecule can quite easily be made because it's just a self-condensation. We have propanal as the nucleophile and propanal as the electrophile. So this was just a self-aldol condensation. Okay, and sometimes our product is going to look a little different. Our target molecule, if it has an alpha-beta unsaturated carbonyl, so if we have a double bond in this position, that also comes from an aldol. One way we can help do our disconnection is we can kind of undo that dehydration reaction and go back to the beta hydroxycarbonyl compound. So if we just do a functional group interconversion, if we add water back in, then we could see the same pattern we saw before, the beta hydroxy, and so our disconnection is at the alpha carbon. And here's now when we do the aldol disconnection, and we come back to our same starting components. This is still the self-condensation of propanal, nucleophile, and electrophile. So we can envision doing an aldol disconnection, whether we have a beta hydroxycarbonyl or an alpha beta unsaturated carbonyl. So let's take a look. At another example of a target molecule that can come from an aldol reaction. We have an alpha beta unsaturated carbonyl. So our disconnection is going to focus on that alpha carbon. We're going to disconnect here. This carbon was my nucleophile because it's my alpha carbon, so I can make an enolate there. And this carbon was my electrophile. If I had a carbonyl there, that would be a good electrophile. So instead of doing a stepwise approach, we could go make the disconnection right on the alpha beta unsaturated. And this is doing an aldol disconnection. And so now I would need this enolate as my nucleophile and this carbonyl as my electrophile. This reaction represents an example of a mixed aldol reaction where the nucleophilic and electrophilic components are two different compounds. And in this case, it would not work very well if I look at the synthesis. So if I just did the retrosynthesis or the planning, the synthesis of this reaction, if I took 3-pentanone and mixed it with acetone and just threw in some base and water, maybe heat it up to promote the dehydration reaction, the condensation reaction, I would get 4 possible products here. I would not get a single product as my target molecule. And the problem in this case is 3-pentanone can undergo a self-aldol condensation where it serves as both the nucleophile and the electrophile. And the acetone can undergo a self-aldol condensation where it's both the nucleophile and the electrophile. And the mixed aldols have 2 possibilities. The pentanone can serve as the nucleophile reacting with the acetone, can act as the nucleophile reacting with the pentanone as the electrophile. So that's not a very good reaction if we have 4 possible products, and only one of them was our desired target molecule. So what we're going to need in a case like this is to have some kind of control over the regiochemistry that we're observing. And there's several different ways that we can achieve that. One possibility is to use LDA. So LDA is a very strong base that would deprotonate. So if I just started with the pentanone and I reacted at first with LDA, I can make the enolate. And so if I just have only the 3-pentanone, I now have just a single nucleophile. Right? There's no competition for where I'm deprotonating because there's only one option. And then after I make the enolate, now I can add in just a single electrophile. So if I use this stepwise approach, now there's only one aldol reaction that could take place, and it's going to give me just my one major product. So that is a good option. Sometimes the aldol reaction works if we have the two components are not equally reactive. So the reaction above used 2 ketones, so there's no way we could get control in that option. But if we have different reactivities of carbonyls, so for example, if we have an aldehyde reacting with a ketone, that is a way we could have some selectivity because the aldehyde is more reactive than the ketone. Remember, carbon groups are electron donating, so the ketone is more electron rich than the aldehyde. It also doesn't, the aldehyde doesn't have sterics as well. And an ester now has an electron donating group on there, so this is even more electron rich. And the amide has a really, really good electron donating group with that nitrogen, so this is the extremely electron rich. And so that's not a very good electrophile. So if we have different reactivities, then that's a way that we can have control over our mixed aldol. So here's an example, and we wouldn't need a stepwise approach. In other words, we wouldn't need to use the LDA approach. So for example, if we use benzophenone and acetone, okay, when we now look for who's going to be the nucleophile, we see that we have only one carbon with one alpha carbon with protons on it, so that's our only nucleophile. The benzene rings here, the phenyl groups have no alpha protons. We can't make an enolate there. And then we do have, in fact, 2 possible electrophiles, right? We have 2 carbonyls, but the benzophenone is going to be more reactive. And so that is going to be the better electrophile. Right? The phenyl group has no alpha protons. So, so there's only going to be one possible aldol reaction, and we're going to get one major product here, major aldol product as shown. Okay, and another thing that we can keep in mind is that our aldol reactions are reversible, and so that means they're going to be controlled by thermodynamics, and we're going to get the most stable product when possible. So we have thermodynamic control in aldol reactions, and that's because they are reversible. So when we look at the compound here, we have an aldehyde and a ketone. Of our 2 carbonyls, we have one that's an aldehyde, so that's going to be my better electrophile. That's going to be the more reactive electrophile, but there's actually 1, 2, 3 alpha carbons that can serve as nucleophiles that could form possible rings. And I'm sorry, we could go this direction. If we went this direction, it would be attacking the ketone carbonyl, and we could use either of these alpha carbons to attack the electrophile, the aldehyde carbonyl. Okay, if we used this alpha carbon here, this would lead to product A, and if we use this alpha carbon here, it would lead to product B. But the major product right here would be when this alpha carbon is the nucleophile, and that's because that product has a tri-substituted pi bond, so that's going to be the most stable pi bond, and it's going to have a ketone product which is more stable and less reactive than the aldehyde. So A is not as good because it gives an aldehyde which is still reactive, so this could do the retroaldol and then close in a different way to give the more stable ketone. And then this 7-membered ring is not as favorable as forming a 5-membered ring, and again it makes the ketone product um, which is actually the ketone is good, but here the 7-membered ring is not as favorable as forming a 5 or 6-membered ring. So that's something else to consider when we are doing an aldol reaction. Is we want to get the most stable product possible if there's more than one that can happen, especially in intramolecular case.